My name is Bruno Ribeiro. I'm here to present a tutorial on G-invariant neural networks. Everything you like about this tutorial was probably created by my student Chandramouli. This is a tutorial of a series of tutorials where we're going to talk about G-invariances and extrapolation and causality. The target audience are folks that are familiar with neural networks and understand basic concepts in linear algebra. Our exposition follows our recent work. If you're interested in more details on representation power, you should look into Jarotsky 2018. Our work focuses on invariances. If you are interested in equivariances, there is a lot of interesting work recently on equivariances, and recommend also looking into those. The concept of symmetry is as fundamental as the concept of a number. Here we have snowflakes, and you can see that they're geometrically symmetric. But symmetry is more than just geometry. If you say two isomorphic graphs are the same graph, then there is a symmetry with respect to permutation of the vertex IDs. All our transformations will be automorphisms. The transformations used in G-invariant neural networks will be taken from one space and leave it in the same space. So if we are considering images, it takes an image as a vector and then leave as a vector, which is again an image. We'll focus our attention on linear transformations today. We recommend reading our prior work if you are interested in knowing how to apply the same ideas to nonlinear functions. We advise the reader to avoid the use of intermediate spaces between the input and the output, say image transformed to a point cloud and back to an image, because that can usually lead to mistakes. Our group transformations will be always automorphisms, so they take from the input space and leave in the same space. So if you take an image as a vector, it leaves as a vector again. So if we are going to rotate the number 4 on the left, first we vectorize it, which is not a transformation, and then you transform the vector into another vector that represents 4 rotated. One has to be careful with transformations that go through intermediate spaces, like you have an image, you make into a point cloud, and then you have transformations over the point cloud and transform it back to an image. So for instance, the work of Cohen and Welling is all correct, but I think a lot of people misunderstand what the work is about. It has G-equivariant for rotations, but of course it cannot be a G-equivariant for translations because image translations are not a group. So what's a G-invariant neuron? A G-invariant neuron is a neuron that is much similar to the standard neuron. We have a set of weights, we have a bias, doing a product between the input and the set of weights, add a bias and have a non-polynomial activation function to get the output of our neuron. And it's the same thing for a G-invariant neuron, except that the weights in the G-invariant neuron are going to be constrained to an invariant subspace. And that invariant subspace is tied to the transformation group that we are of interest to be invariant to. So this invariant subspace is one such that if you compute an inner product between the weight vector in the invariant subspace and the weight vector in the invariant subspace, but then before you apply a 90-degree rotation, this invariant subspace, if it's invariant to the 90-degree rotations, then it's going to give you the same output, both inner products. Let me show you an example we have here. For visualization, we will unvectorize, but actually everything here is a vector. So the inner product between this as a vector and this as a vector, this is the input, these are the weights. And if we do the inner product between the two, we get this number. If you rotate, we get the same number because this weight vector here belongs to the invariant subspace. Hence, the output of our neuron will be the same no matter whether the input image is rotated or not. This is because all weights in the invariant subspace are going to be left invariant if right multiply them by transformations from the group. For instance, here we get some vector in this invariant subspace and we right multiply it by a 90-degree rotation, and then we show it this unvectorized version here, and we can see that the vectors remain the same. So the question now is, how do we construct this invariant subspace? That's what we're going to see next. First, if you're interested in skipping parts, you can skip parts. We'll talk about what's a group, what's a transformation group. And then we'll talk about the Reynolds operator of a group, subspaces of a vector space, bases and dimensions. Then we talk about the eigenspace of a linear operator and the invariant subspaces. And the linear operator is going to be our Reynolds operator. And finally, we finish with step-by-step examples with Python code showing how we apply G-invariant neural networks to graph inputs and image inputs.